Good afternoon. This is Peter Grover, Distinguished Member of Technical Staff at Renesas Electronics Corporation. I'm going to be presenting some slides on a generic voltage or current monitor for mixed signal designs. So this is a monitor that will enable you to probe currents or voltages in AMS or DMS without the user having to actually change any of their code. Basically, their class-based test or their setup can instantiate a monitor, and irrespective of the actual data type that monitor points to, it will work. So to get started, we're just going to cover the problem statement. So the problem we've got in the current mixed signal space is normally you either make something that will work with AMS or you make something work with DMS. And if you change the abstraction of the net that module is connected to, you normally then have to change the module that is connecting to it as well. And with things like a netlist configuration, it's very easy to change the abstraction. So it could be that in one configuration, a node resolves to real, in another a UDN, and another electrical. And really, you want the ability to be able to place down a monitor that is looking at that node all the time, and irrespective of whether that's a real, UDN, or electrical, the monitor carries on working. And we might also have the use case where the node might not exist in some configurations. It could be that you've bound that instance out of the netlist because you are doing some AMS performance things and that block's not key. It could be that the node that you're wanting to monitor can't easily be monitored from the .io. So if we take a classical chip, it could be there's some internal reference. That reference could have a big kick on it, but you can't see the effects of that externally because the analog control loops, etc., mask the effects. But actually, that kick is important. You need to see what's causing it, when it's happening, to root cause the problem and also fix it. So what I wanted to be able to do was monitor not only voltage but port current and maybe port block power. So I've got a way of having all these checks on running concurrently. So there's always a wish list with this. I don't want to use a hard-coded path because, as we know, a hard-coded path A forces the data type, B, if it doesn't exist, is an elaboration error. So basically, I need to pass in a string. And that string could be a concatenation of other strings. It could be a parameter. I want it to work in DMS and AMS without user interaction. So I want my verification engineer to place one of these down and not have to think about whether the net is electrical or a UDN. It just works. And during the simulation, I want to be able to change trigger levels. I want to be able to enable, disable this monitor. And key thing with all of these sorts of things is you really want to limit the overhead that you place on the simulator. I mean, it's great building these monitors, but if you place so many down or they're written badly that they actually consume more than the actual design, we've got a fundamental problem that needs addressing. And what I've actually done also is UPF has limitations when it interacts with DMS or AMS because UPF is really designed for pure RTL levels. So this monitor we've also used for UPF monitoring. So I apply one of these monitors to a net. It returns to say whether the supply width is in a certain range or not, and I can use that digital signal to then trigger the UPF supply being present or not. So this works around some of the limitations that are within the UPF standard as of today. So what I really wanted to be able to do is monitor some internal signal. Now, the classic one that most chips will have is a band gap. So you turn the band gap on. You want to be able to monitor it because ideally it stays at 1.2, but it could be you turn on some component of a circuitry and that kicks the band gap, but not enough to notice it. So what we want is to be able to put a monitor on there that should never trigger, but if it does, it's something that we need to look at. And the nice thing about this is the way we're describing this monitor is it will allow lots of concurrent checking for any simulation. So you could place these down on every BIOS, every reference node, and then and dynamically turn the enable on for this monitor when you know that that reference should be there. So you've got a way of covering more of the verification holes that aren't present. As the second bullet point states there, sometimes kicks or noise on these internal nodes are really hard to see unless something catastrophic happens elsewhere in the circuit. And this basically poses a verification hole. Imagine something kicks the band gap enough, but it causes a pound reset. Great, you can detect that. But if it kicks it enough, but not enough to cause a pound reset, and not enough to see it externally, you've got the possibility that across corners, etc., that you do see that in the real device. We could use it to monitor static bias currents into a block. So you're trying to check that you're getting 1 microamp into a block. You could easily just go every time that block's turned on, constantly monitor the bias. If it goes outside of the 1 microamp plus or minus some tolerance, then let me know. And again, this can be done all concurrently. So every time you re-netlist or pick up design changes, your monitor's already there. And the nice thing is you can do all of this in DMS, but it's not as important. Everything's an ideal model, so really your band gap should stay at 1.2 volts. But what you can do is use DMS to debug the setup, get the monitors all working in a fraction of the time, so that when you run your more costly AMS simulations, at least you've set up these components correctly. So here's just an example of what you can do. Let's just get a pointer. So I've set a upper threshold and a lower threshold, and this is my signal that's just doing some sort of sawtooth effect. And at this point here, I've turned it on. And as long as the signal stays within this range, it's okay. But as soon as it goes out of range, I want it to trigger an event. And that event could just then call a dollar display or a UVM message, or it could actually be used in the rest of your test case to do other things. So there are a few limitations on this setup. Because we're using Verilog AMS, it has to be a module. Because it needs access to the continuous time nodes, and that's only available in a module. It utilizes in AMS the analog node and port alias functions along with the VPI. It takes in 2 parameters, a node and a mode, and we've got this optional one that says if this node only exists in DMS, then don't worry. If it's an AMS sim and it doesn't exist, or if it's AMS only and the node doesn't exist in DMS. So you could do all of that filtering to sort of make it really slick that if the node's not found, it doesn't create an error, but you could choose what you want to do. So the way this works is you end up with a system Verilog wrapper layer, which has the API and all the class-based stuff. Currently, you can't put that in a Verilog AMS file, so this is why it has to be done this way. And going forward, this is sort of the proposed way of dealing with real numbers or AMS sims and DMS sims. So here I've got a Verilog AMS module. Now I could have a system Verilog version of it that just sets ananode OK to be 0. And that allows you to, be able to use this whole setup in pure DMS as well as AMS. This is just an optimization so that you don't take an AMS license for literally this block of code that is just going to set a variable to 0. So it's totally up to you. As I said, this is currently matching the UVM mixed signal proposed architecture, where you have a system Verilog wrapper, and then you have the core modules that deal with the abstraction. And then the API is connected via what we call a proxy. So this is something that might come out in the next 6 months with UVM mixed signal. So what happens is the analog initial block is called first, and this is how an AMS simulation starts. It will check if the node is electrical and set analogue OK variable accordingly. Once all the analog initial begin blocks have been processed, control is passed to the digital engine, and the digital engine will trigger the digital initial blocks. It calls a function get analogue OK, which doesn't actually exist in there, but due to upscoping, it will look in this system Verilog wrapper layer. And then it will call the same function, the Verilog AMS module, to get the analog owned variable, because this variable here is going to be owned by the analog engine. Therefore, you can't do an out of module reference from the system Verilog wrapper layer to the AMS one, but you can call a function that then queries the analog owned variable. So it's just a bit of a trick. So if the return value is 0, then the node is not electrical or does not exist. So we want to try DMS. And we do this using the VPI to register a callback. If the dig node OK is 0, you could basically go, the node doesn't exist, it's not digital, it's not analog. So if you're expecting that net in your design, you'd probably want to error out at this stage. So that's why I said it depended on this extra parameter to say whether it's AMS only, etc. Assuming one of them does go high, then you can start your transient sim. So within Verilog AMS, we have $analog node alias and $analog port alias functions. These are called within the analog initial begin. So what happens here is we've got an internal electrical node called int node. The analog initial begin sets analogue OK equal to 0. Then depending on the mode, it will call one of the functions. So if we're doing potential, what this analog node alias basically does is put a 0 volt voltage source between this net and the one referred to by the string. Similarly, an analog port alias will put a current controlled current source between that on that port there, and bring it into here. Then this is the function that would be called. It has to take an input because Verilog AMS is based on the 2004 system Verilog standard, and this still needed it. So it's not used, but basically this can be called from the digital, and it returns the value of the analog node OK, which is being set here. And then a bit later on, we'll go through the analog begin and end where it does the monitoring, but assuming the anode is OK and based on the potential, it either probes the voltage or it probes the port current. Unfortunately, system Verilog has no digital node alias or digital port alias function. Vendors don't have a generic version for every net type, so some vendors will have real net versions or specific UDN versions, but there's nothing out there that will work with any net type. Direct access, which is a common thing that verification people would do, would force an AMS connect module or a net type conflict in pure system Verilog. Then there's the next problem that in digital there's no native current probing in the system Verilog UDNs, you need to know the knowledge of the user-defined resolution. So some vendors supply like an ENet, which is meant to model electrical behavior. There's currently no way of doing port currents. There is a paper that was presented at CDN Live last year, which shows how you can do this and create a port current in DMS as well. So really the solution with the digital side is not to use any of the system Verilog functions, but basically use the Verilog programming interface to access the data objects. That makes this far more expandable to any other data type. So if you had various different UDNs, it could support that. If you had a mixture of UDNs, reals, WReals, etc., it could support that. So the way the VPI works is you write your C program. The VPI is a set of routines that via the PLI allow you to query the simulator. So you can pass it a string and go and get me the handle to this object. So assuming that path exists, it will return to a handle to that object. You can then go, what object are you? So is it a module? Is it a package? Is it a class? Is it a net? And from then on, you could go, right, if it's a net, what type of net are you? Is it in the discrete domain? Is it in the continuous domain, etc.? So you've got the ability to do lots of things. And the nice thing about it is it's all LRM compliant. So a lot of this then doesn't tie you to a single vendor. So we have to do a bit of work in the VPI layer. We first of all have to import a custom C function, which I've called DPI UDN change callback into the system Verilog layer, and that is called within this set UDN change callback function. So this line here, import C, basically says this function that you'll detect in the VPI layer maps to this function when called within system Verilog. So we can see here, system Verilog function is being called here. That would basically go and call the VPI routine. So I've wrapped this up because this takes in a string, which is the UDN net, an error message, and a scope. So the UDN net is the string to the user-defined net type you're wanting to look at, and it has to be a scalar. The error message is a string that's returned from the VPI layer. So if anything goes wrong, it will display the message in the system Verilog land rather than just natively in the C. So you've got the ability to use UVM reporting, etc. The scope is something that's needed, and it has to match basically $S format F%M. I can't have a default value because otherwise it takes the default where the function is. But the scope input basically is saying when this function is called, this is the current location in the hierarchy. And this is needed because what this VPI function will do is monitor that net. And when it changes value, it goes and looks for a specific task in this scope to go and execute. So we'll see that on the next slide. So as I said, we can query stuff. So here I've got VPI handle by name. It takes in a path, and that will return a handle. Now I've simplified the code here. You should do lots of error checking because that path might not exist, or there could be other problems. Here I happen to know it's a user-defined net type, and a user-defined net type is a structure. So you're going to need to iterate over all the elements of the structure. And so what I've done here is when one of the elements of the structure happens to have the name V, I go, right, that's obviously something I want to monitor. And basically I build a callback routine. So there's a type for callback data. You can give it a reason. The routine, it will run when that event happens, and you can do times and other things like that and include user data. So first of all, we set the time, we set the format. So here we've set the reason to CB value change. So that says whenever the element of the V, real V of the UDN changes, this will generate a callback. The callback routine is this C function here, and then I basically pass in the address to the time and value. And then what I've done here is in the user data is I've passed in the scope value. So that's basically passing in a string. So, and I copy it all in and then I register it there. So now what I've got within the simulator is something that is looking at the path to this UDN, the V field, and additionally we can do the R field. And if they change, it basically will go and look at this C function here and execute that. And we'll see that on the next page as to how that works. So imagine the UDN does change. This is the C function it would call. It gets the scope from the user data, because remember on the previous side, we went and put the scope in the user data area. This line above is just setting the size for it. We set the current scope, and then basically I'm calling this DPI update UDN. It's declared as a void function in the C layer. But what I'm doing is I'm exporting basically this task to map to this C function in the C layer. So this then means when that's executed, this line here basically links that up to this task here, and the scope basically says where in the hierarchy it should find that. So the UDN changes, it triggers this returns a 1. This causes this code to be executed. If the monitor is enabled and it's a digital node OK, then basically it toggles this node changed event. We use a non-blocking event here, and that's quite key. When user-defined net types or even real nets or logic nets, they could change values multiple times during a delta cycle. And really, it's only the final resolve value that you're interested in. So this non-blocking event basically makes wait until you've done all the active region of the simulator, and then you start looking at scheduled events. And then this would trigger the always at node OK, and then we can get the value based on the mode. Again, you would have to use the VPI, otherwise it's an out of module reference. So there have been presentations in the past on how you can get the voltage of a net using the VPI routine. And that paper I mentioned earlier about getting your current probe in DMS, that also explains how you do this. So on the AMS side, what we can do is we generate our monitor code. So here I've generated a very simple monitor. If the analog node is true and it's enabled, then basically based on whether it's a potential or a flow, I get the value, which is a real. And then just checking if the value is within a certain range. And you must have hysteresis in Verilog AMS, otherwise you can cause oscillations. And that basically sets an integer that's internal. 0 meaning it's not okay, 1 meaning it's okay. Clearly, if the analogue node OK is not true, or enable is not true, then you should also say the in range is not true. Then this line here basically will be monitoring the analog owned in range int A, and every time it changes value, it basically will take a copy of that and place it into the discrete domain. So now you could then monitor in range int in your system Verilog layer, which is exactly what you want. Now, often you see people not doing if-else code like this on comparators, which is fundamentally what this monitor does. They use above statements or cross. They're really not needed because you don't care where, you don't really want to create an analog time step at exactly the time the signal goes out of range. Just the next time step is good enough. There's no point in waiting all those CPU cycles to create a time point just as it crosses the threshold, because that gives you no more information. So it's better to use above or cross. If you really want to get when the time happened, you can use the last crossing function, which will do a linear interpolation and tell you the exact time or the closest time to when it actually violated one of these conditions. So the DMS monitoring code, as I said, would be triggered on this node change non-blocking event, which would then call the node this always block. Again, we'd check if it's enabled and digi OK, else we would say it's not OK. Then, depending on the mode, if it's potential, we call some VPI routines I've written and I have presented in the past. Get voltage from path that would take in the node. This is the return value and what to do if that fails. Clearly, this shouldn't have failed because that node there should have passed our previous checks. Then we've got some functions to see if the value is X or Z, you know, the real X and real Z states that most simulators support. Else, it just says whether it's higher or lower. Here, you don't really need hysteresis because it's either right or wrong. It's not like an analog solver that iterates over Newton-Raphson to get a solution, and so each Newton-Raphson could trigger it or not trigger it. Then finally, in the system Verilog wrapper layer, we can use a always block to monitor those in range int flags. So here you'll notice it's always begin. There's no @ sign. I've basically put the @ sign behind a condition. So if analogue OK, then it's basically waiting for the instance of the AMS monitor core, and it's looking for the in-range int to toggle value. And I'm basically also gating it with the enable there, so that this process is highly optimized. Then every time that in-range changes, depending on what it is, you could either say it's an error or you could say the mode is in-ranged. Else, if it's digital node, we would then start monitoring basically the DMS monitor and the enable. Apologies, that begin should be down there to make it more readable. And then just the same. And then finally, we've got the else branch, which is analogue OK or DMS monitor core dignode OK. And this is because this process could have started before, say, the dignode OK has been set, and so you don't want to get stuck. So this just guarantees that the module works under all ways that a circuit can be initialized, because digital initial blocks can be executed in an indeterministic way. Always processes can also start up in an indeterministic way. So in conclusion, while the presentation has gone on a very classical high-low checker, you could expand this to do more dynamic checks. You could do rise and fall times of signals on a code change, envelope tracking. You could make your own sine wave detector, etc., that would work in both AMS or DMS. The key thing here is your checker or your monitor is going to be very bespoke to the application. You can't write something that is going to work with every possible use case. There's just too many. So take a look at what you need to do. I've started with something as simple as a band gap and references, because I think that is where we're going to get the most value out of this. But the key thing here is that This really does enable a sophisticated concurrent checking system for analog intent signals. So currently, I bet a lot of people just have to look at the bandgap signal in their waveform viewer, and you become a bit blasé, just constantly looking at the same signal that you know will never change. This is a way of just placing a monitor onto it and going, right, from now on, we don't need to worry. As long as the monitor's been set up, we'll track it. So if you want to know more, the only two books on the VPI or the PLI layer and how you do the communications are up on screen. What I would suggest is, if you are going down this route, is first of all sync up with your EDA vendor. It may be they've got some of these routines available for you, or they might want to work with you on building them. I hope you enjoyed the presentation.